So the next part of this unit is not looking at electronic structure. Now we're looking at the nucleus and the nuclear structure and nuclear properties. So one experiment we talked about in the chapter 7 or topic 7 was Rutherford's gold foil experiment, which helped us determine that an atom actually has mainly empty space and a nucleus that is filled with positive charge. So if you want to remind what that experiment was, he used a radiation source that emits alpha particles, and he directed that ray of alpha particles at a thin layer of gold atoms. Now, in Thomson's plum pudding model, we would have thought that those alpha particles would have went straight through, as shown over here. But what he actually noticed, or Geiger and Marsden, his graduate students noticed, was that most alpha particles went straight through, but a lot of them actually deflected off of that surface. So the majority of the atom is empty space. That's why the alpha particles are going through. But there's some significant repulsions happening here to create scattering. This is that detector, a zinc detector. Wherever those alpha particles would hit, it would glow. So they were able to map out the deflection angles. So this experiment was really important to help us understand the structure and size of a nucleus. And what again, to summarize, Rutherford was able to say that the electrons were out in this empty space, whereas the core nucleus has to be dense and positively charged and very small at the center of an atom. These alpha particles, the closest that they can approach before they deflect would depend a lot on their kinetic energy. And what we're going to do now is show some calculations that you'd have to do in HL physics to estimate the closest approach that alpha particle would have before it deflects. So in further experiments that they did is they took that alpha radiation and they put it in what looks like a lot like the electron gun, except in this case it would be an alpha particle gun. And so if I place the alpha particle source in between these electrodes with a hole in it, and I apply a potential of 1,000 volts, I can accelerate that alpha particle and change its kinetic energy. So in future experiments, what they did was they ended up changing the kinetic energy, and they wanted to see how that would affect the angles of deflection. So as they increase the kinetic energy of the alpha particle, it should approach closer, and what would happen? Could they smash the nucleus? Well, they all end up going straight through. They wanted to see what would happen. So the idea here is that the alpha particle would get really, really, really close, and then eventually it would repel the other nucleus and start to scatter. So if I change the kinetic energy, I can get as close as possible, and we can start to probe what size that nucleus of a gold particle would be. So in a gold nucleus, we have 79 protons. That's a lot of positive charge that's repelling. In an alpha particle, we have 2 protons. And so how would we model this mathematically to measure the closest approach? Okay, so if I can calculate the kinetic energy of an alpha particle based on this setup, that kinetic energy is going to be converted into electrostatic potential energy at the point at which it stops. So if I subtract these two things, it should equal to 0. If I go further down, what we'll see is, this is how I would calculate the kinetic energy of that alpha particle. We've done this before in electron guns. So 1,000 volts, the voltage, times the charge of the alpha particle. In this case, the alpha particle has 2 protons, so that would be the charge of 2 protons. So 1,000 volts times the charge of 2 protons, 1.6 times 10 to the minus 19 coulombs times 2, is going to be equal to K, that's Coulomb's constant, times the charge, 79 times the charge of a proton, times the charge of an alpha particle, divided by R. And R would be the distance of closest approach. That would be, if I drew this, if it stopped here, if that alpha particle stops there, that would be R. R would be that distance of closest approach. Okay, and if I rearrange this equation, I can solve for that distance of closest approach, where K times the charge of an a gold nucleus and the charge of an alpha nucleus divided by voltage times charge of the alpha nucleus. You can see these two would cancel out. So that's kind of cool. We can solve for the radius just from these 3 variables alone. So here, let's put this knowledge to practice. Here's an example problem from your SOCOS textbook, which is the first problem I want you guys to calculate for homework. An alpha particle is fired head-on at a stationary gold nucleus from far away. Calculate the initial speed of the particle so that the distance of the closest approach is 8.5 times 10 to the minus 15 meters. Take the mass of an alpha particle to be that. Okay, so here's another diagram. That would be the distance of closest approach before it deflects off. We don't know the velocity. We're trying to find the velocity of that alpha particle. We know the mass of that alpha particle. It's written right over here. And we know that the gold particle has 79 protons. So like I said before, kinetic energy will equal to electrostatic potential energy. And here was the relationship over here. Now in this case, I'm not using voltage times charge. I'm using the actual formula for kinetic energy. 1/2 mv squared is equal to k q gold q alpha over r. And then if I rearrange and isolate for v, I end up getting this relationship. So you can always pause, try to work out the algebra. And then if I plug numbers in, I'll be able to solve. So k is 8.99 times 10 to the 9, 79 protons, the charge of a proton, 2 protons in an alpha particle, the charge of a proton. That is the mass of an alpha particle, and that is the radius of closest approach. After plugging that in, we should be able to solve the velocity, which is quite fast. Okay, and this answer is in the back of your Tsokos electronic text. All the answers to your test yourself questions are there. That's part of your homework. I want you to prove these answers. Okay, so this would be just an example of maybe a calculation you can get on an IB exam where they want you to find either the closest approach or the velocity of an alpha particle or the accelerating voltage. So it's worthwhile practicing this setup.